All right, everybody. Class recording has started. So, today, you took your quiz. If you go to the calendar, okay? You took your quiz today. The rest of today, we get into the next unit in the chapter, or the next part of the chapter, which we started yesterday, dealing with electrical potential energy. We'll review that, then we'll talk about voltage and current today. That is our plan. I won't see you guys until Thursday, but at the beginning of the class on Thursday, we will finish off the outline that we're going to start today, because we're not going to get all the way through it today. Then, the second half of the period, we are going to head down to the library and do your lab for this section, but your lab is a virtual lab. So we'll be down in the computer lab. You'll be building some circuits on there, looking at the effect of different changes to those circuits. I think it's pretty cool. I think it's a pretty good website and does a good job of explaining these topics. So hopefully you will as well. Then, on Friday, we will do the outline as far as circuits go, hopefully reinforcing a lot of the things that you will see in your lab on Thursday. That leaves us Monday to wrap it up and review, and then test on Tuesday. Okay. Questions about the calendar? All right. Yesterday, we finished up the first outline, and the first outline deals with electric charge, and what it is, and how we measure it, and how it responds in certain situations. But this section, we want to start getting into what do we do with these charges? And our discussion about what we do with these charges started with this word, energy, right? What was our definition of energy? How did we sort of define energy as far as our working definition? Katie, go ahead.
The ability to do damage.
The ability to do stuff, the ability to do damage, the ability to change things. And we find out that these electric charges have that ability in certain situations. Okay? So, the first topic that we introduced yesterday was electric potential energy. The fact that it is a kind of potential energy means what? What is it based on?
Location.
It's based on location, right? So, if we go to this picture here, this is a picture that is similar to the one that's in your outline. First, big positive charge over here on the left, big negative charge over here on the right. Okay? Arrows in between those two charges representing what? What did we say the arrows represent? The electric field, right? The area around the charges where it can affect other objects. Are those arrows consistent with what we talked about as far as the electric field yesterday is concerned? Right? On your quiz, you had to answer a question about field lines, right? We said that that's how they're supposed to point, correct? Okay. So, let's say we take this charge and we'll make this a positive charge. So let me group these together so they move with each other. Okay. So we take this charge and we move it like that. What did we do to the potential energy of that charge? Okay. We increased it. Why, Maddie? What is that charge going to want to do now?
Move to the negative side.
Move to the negative side because it repels positives and attracts negatives, right? Okay. So, Katie, you asked a question to me before class started about a homework problem from last night, right? Okay. This was on page, hold on a second, page 545. And this is question number 3 from page 545. So it says, predict which way charges are likely to move between positions of different electric potential energy, one high and one low. Okay? So, in this case, this spot where I have drawn this charge right here, is this a spot of high potential energy or low potential energy? That's a spot of high potential energy. So, if we leave this charge by itself, what is it going to do? Is it going to stay there? No. It's going to move how? To the negative side, which would be a spot of what as far as potential energy is concerned? Low potential energy, right? So I'm not exactly sure how this question is worded, kind of weird, okay? So generally, charges are going to move from areas of high potential energy to low potential energy on their own, okay? That's no different than this baseball, okay? So if I take the baseball and I raise it up in the air, what am I doing to its potential energy? Increasing it. What kind of potential energy? Gravitational. Will it stay here on its own? No, it falls down. Because what happens to its potential energy as it falls down? It decreases and turns into what? Kinetic energy. Good. This positive charge, if I move it from here to here, it won't stay there on its own. It'll fall back down here. Can I get it to move from here to here initially? Yeah. Okay. Can I get this baseball to move from the desk up to here? Yeah. Okay. That's a different story. Hold on to that question just for a second. But to use terms that we're familiar with, what do we call it when we increase the energy of something? We say that we do work on it. Okay. So Joe, we have to do work on this charge. Okay. So there is different ways you can get it to go. One way you can get it to go is if there's a chemical reaction that occurs in here, it can cause objects to move from low potential energy to high potential energy. Okay? The reason I bring that up is because it's going to be relevant to what we're going to do later on today in the period. Okay? So there's different ways you can do it. Physically, like we could just take a really stronger negative charge and kind of pull it across if we needed to and then get rid of it, and then it's high potential energy and stuff like that. But a lot of times we do it from a chemical standpoint. Okay? All right, are we good with this so far? Okay, Farah, go ahead.
I understand everything you've been saying, but
Okay.
I still don't know why the positive charge has more potential energy by the positive side.
Because what do these two charges do to each other?
Repel.
They repel. So as they repel each other, if we bring them closer and closer together, do they like that? It's harder and harder to bring things of the same charge closer together because they repel each other more and more and more, right? The force that they exert on each other, we said, was inversely related to the distance. So as we get them closer and closer and closer, what happens to the amount of force that they experience on each other? It increases. So it's harder to push them together. And if we let them go, this thing is going to go whoosh, like that. Just like if we let the baseball go, it falls to the ground. Does that make sense? All right. Good on this as far as review from yesterday. All right. Let's pick it up from there. The amount of electric potential energy that an object has depends on three things. The first row here is the formula that we use to calculate electric potential energy. I won't hold you responsible for that formula. That's a physics thing, okay? But as far as the factors that are concerned, that's the part that you need to know. So, things that influence potential energy. First, how big of a charge are we actually moving around? That yellow dot that we were just playing with on the screen, how big of a charge is that? Because that's going to influence how much potential energy that object has. Very good.
These are under G, right?
Yep, under G. Okay. Then, the next thing that influences how much potential energy it has. How strong of a field are we actually moving it around in? And then the last thing that influences the amount of potential energy is, okay, how far are we moving it in that field? Those three things combined will go to determining how much electric potential energy a charge has in an electric field. Good there?
When you say about the charge, did you say this how big the charge actually is?
Let me go. I'll go through all three of these things here in just a second. Okay. Okay. So we said there were the three things that influence the amount of potential energy that this charge has. So the first thing, let's say this thing, this yellow part, we actually make it bigger. It gains more and more and more, or let's say it loses more and more electrons, so it becomes more positive. If I take this bigger positive charge and move it here, how much does it want to repel the other positive charges that are there? More positive charge wants to repel more positive charge more. Right? I know there's a lot of mores, but okay. So the value of the charge relates to how much unbalanced protons, electrons are in this. Okay? The second part, the size of the field. There are 5 arrows here. Coincidence? Maybe, but there's 5 positive charges over on the left-hand side, and then 5 negative charges over here on the right-hand side. So 5 arrows. But let's say I get rid of like this positive charge and this positive charge and this positive charge. And now there's only 2 over here. What's that going to do to the number of the arrows that shows up in that space? It's going to decrease the number of arrows. I suppose logically we could say if we get rid of 3 positive charges, we get rid of 3 arrows, and now there's only 2 arrows. If there were only 2 arrows left, and I moved this from here to here, would I still increase its potential energy? Yeah. But if there's only 2 arrows, is it as much of an increase? No. So that's the whole strength of the electric field part. Right? Then, movement of charge. Instead of moving the charge all the way, let's say I only move it halfway. Did I increase its potential energy? Yes. Yeah. Did I increase it as much as moving it all the way across? No. So those are the 3 things that influence how much potential energy that object or that charge will have. Good? All right. The next part might sound confusing at the beginning. The next topic is potential difference. But we'll see that it's not exactly the same thing. First, by definition, potential difference tells the ability of an electric field to change the electric potential energy of a charge. The potential difference tells the ability of an electric field to change the electric potential energy of a positive charge. That's what it says in the book. As far as a working definition, or maybe a little bit more explanatory, right? The potential difference is how much of a difference is there in electric potential energy if I move this charge from position A to position B. So a lot of those factors that we were just talking there about in the last little section influence potential difference as well. But now we're talking a little bit more about the field itself. Good there as far as definition goes. Sometimes, most of the time, we refer to potential difference as voltage. Voltage and potential difference are the same thing, synonyms. We measure potential difference with the SI unit of the volt, capital letter V. Volt is a derived term, or a derived unit. It is a combination of these 2 units. 1 volt is equal to 1 joule over 1 coulomb. joules. Energy. What did we say we measured in coulombs? Electric charge. So here, if we have joules over coulombs, we're talking about how much energy does each charge gain. That's what voltage tells you. How much energy will a charge gain as it moves through an electric field? Is that good as far as definitions go? Okay. Let's example a little bit. There is a big picture at the bottom of your outline in page 2. Notice there's a lot of space around it because we're going to fill in some details around the edge to talk about this picture. Alright, so there's the picture. First thing that you guys don't have on your picture, but that I have in this picture, is that this component on the bottom, right? What is that a picture of? That's a battery. Okay? But inside the battery, what have I drawn here? Arrows representing the what?
Electric field.
The electric field. There is an electric field inside of the battery. Okay? Joe, this is where you talk about it. There is a chemical reaction that occurs inside of this battery, and it causes an electric field. Okay? First, are the arrows consistent with what we talked about in terms of electric field yesterday?
Yes.
Because they point from where to where?
Positive charges.
From positive charges to negative charge. Okay? Now, let's take a look at an electron. Okay? So I am going to change it up a little bit. All of those examples that I gave you before, I was moving a positive charge around. Yes? But now we're going to move a negative charge around.
Why?
Because electrons are what actually moves around, right? So, here's my electron, and I move it from there to there. I have moved the electron closer to which part of the battery?
Negative.
The negative terminal. What happened to the electric potential energy of that electron? It increased. Okay? Kitty, back to your question from homework. This is a high potential energy state because what do we have close together here?
The two of the same charge.
Two of the same charge. In this case, they're both negative, but it's the same thing, right? So, electrons move inside of the battery and they gain electric potential energy. That's what a battery does. There is a chemical reaction inside of this battery, and it causes electrons to gain electric potential energy as they move through the battery. If we go back to trying to make connections to gravitational potential energy, electrons moving through the battery and gaining potential energy, what is that the equivalent of? If we talk about it from a gravity standpoint, that's me picking the ball up, right? Okay? That's what the battery does. It picks the ball up, or it gives the electrons more electric potential energy. Okay? What term did we already use once today that also describes what that battery is doing? It does work. The battery does work on the electrons because it increases their potential energy. Is that good? You see how these things are all sort of fit together? All right. Do those electrons like being in that position? No, it's a high potential energy state. They want to get back to the other side of the battery, but the battery is constructed in a way that they don't just slide back across the battery, because that's not good for what we want it to do. So instead of sliding back across the battery, there is a path that they have to get back to the positive terminal of the battery. That's these wires. So that electron moves out into the wire. By moving the electron away from the negative terminal of the battery, what's happening to its potential energy? It is decreasing. But as the potential energy decreases, what do we find happens? Kinetic energy increases. Those charges start moving. That's the equivalent of me doing what with this baseball? Dropping it. That's what happens when they move out into the wire. It's the equivalent of me dropping the baseball. Potential energy is decreasing, kinetic energy is increasing. Good there? As they move through this wire, they continually lose electric potential energy. But sometimes it doesn't just turn into kinetic energy. The light bulb is there to take electric potential energy and turn it into other stuff, like light and heat. If we're talking about a speaker, right, like your little battery-powered speaker that you plug your iPod into, right? What does it turn the electric potential energy into? What kind of waves? Sound waves, right? Turns it into sound energy. The components that are attached to the battery take that electric potential energy that the electrons have and turn it into other kinds of energy. Eventually, where do these charges end back up?
On the right side of the room.
Eventually, they end up back at the positive terminal of the battery. By the time they get back to the positive terminal of the battery, what has happened to all the electric potential energy that these objects or these electrons had? It's gone, turned into other stuff. But then, what does the battery do? It does what on those charges? It does work on those charges and then increases their electric potential energy again. That would be the equivalent of me doing what? Bending over, picking the ball back up, and reaching up, putting it back up in the sky. And do it again. Do it again. Do it again. Do it again. Can the battery do that indefinitely? No, right? What happens to the battery eventually? It goes dead, right? Just like me. Can I continuously just picking the ball up, reaching higher, picking the ball up, reaching higher, picking the ball up, reaching it higher? Eventually I'm going to get tired. Well, I'm going to die eventually, yes. Eventually I'm going to get tired and I can't do it anymore, right? Joe, that's the chemical reaction inside of this battery basically running out. So it just can't increase the energy of those electrons anymore. That's how the battery does the work. It's a chemical reaction. I do the work physically on this baseball by picking it up and reaching it in the sky. But if I don't eat anything, eventually I can't pick it up anymore. Does that make sense? Okay. Are we good with this? Questions as far as this goes? Okay. Let me introduce the next term, and then that'll get us into tomorrow. Okay. So, last part. This is kind of the important part. The potential difference, or the voltage of the battery, remember, potential difference and voltage are the same thing. The potential difference, or the voltage of the battery, measures the difference in the electric potential energy of the electrons at each terminal. So the voltage of the battery tells me how much electric potential energy am I giving each electron as it travels through the battery, which is also the amount of energy that it can then use in the whatever it is that we're running in the electricity through. So potential difference, or voltage of the battery, measures the difference in electric potential energy at the different terminals. How much electric potential energy do those electrons gain as they go through the battery, and then how much do they lose as they go through the circuit? How's that?
That was great.
Good. I'm glad you enjoyed it. So, all right. This seems like a good time. This is a convenient stopping point for us. So we will pick it up from here tomorrow. Hey, if you check the calendar, there's no homework on it tonight. I will fill in a couple of problems that relate to the stuff we talked about today, but it'll relate to Thursday.